Hello, welcome to a video about mechanical waves. We've got the learning intentions on the left hand side here. This section is going to be broken up into 2 or 3 videos. In this video we will just focus on the first learning intention and the first success criteria. So mechanical waves such as sound and seismic waves transfer energy through a physical medium, and in stage 1 physics you'll need to be able to explain a range of wave related phenomena including echoes, refraction and resonance using the mechanical wave model. So a quick definition: mechanical waves are progressive waves that propagate outward from their source and transfer energy via a physical medium. So that physical medium can be a solid, a liquid or a gas. These waves are modelled as oscillations of particles about a fixed position in an elastic medium. So it's the material or the medium itself that the particles of it are oscillating or vibrating. However, the wave itself is the energy that causes this vibration. An elastic medium just means a medium that returns to its normal shape after a stretch or a compression, so it reverts back to its original shape. Seismic waves are mechanical waves that propagate throughout the Earth's layers. So the Earth's particles oscillate. They can oscillate parallel or perpendicularly to the direction of propagation, and the particles of Earth collide, transferring energy. So in seismic waves, they'll propagate out from a focus point, and this might be somewhere along a fault line, so it might be between a couple of tectonic plates or something like that. Sound waves are a series of compressions and rarefactions that propagate through a medium. The air molecules oscillate back and forth parallel to the direction of propagation, and air molecules will transfer energy via collisions between each other. So, for example, here in this image, the sound wave is travelling this way, and each of these particles is either travelling this way to the left or this way to the right, and that will change for each particle depending on what position they're in relative to the sound wave travelling through. So each of these concentrated positions here, so where all the air molecules are concentrated together, is called a compression, and then the parts in between, so where the air molecules are least concentrated, these are called rarefactions. And these vibrations of air molecules will propagate until they hit the eardrum of someone's ear. Echoes occur when sound waves are reflected from a surface and then they return to the source of the sound. So waves are reflected from a surface and they'll change direction, and the energy is propagated to and from the source via oscillation of medium particles. So just like the medium particles will oscillate in a regular sound wave, they will oscillate for a regular sound wave and a reflected sound wave. When these reflected waves are meeting with the original sound waves, they will just travel through each other. So at any given point, the particles will oscillate in the net direction as a result of those two sound waves travelling through each other, one reflected and one original. So echolocation is used by animals, and they will emit sound waves, and these sound waves that they emit will then be reflected back by the surface of their prey or their food. So the animal that emits the sound wave will then interpret the distance and the direction to the animal or the surface of the animal that has reflected their sound waves. And they'll do this by measuring the time delay between their emission and their detection of those reflected sound waves. And this will just happen automatically in the animal's brain, so they don't consciously think about it, but they will have evolved to detect and interpret how far away their prey is. You might get a question that asks something along the lines of determining the speed of a wave when you're given the distance between the emitting animal and the reflecting animal or the prey. And you might be given the time delay as well. So, for example, if the distance between a dolphin and some fish that they've detected is 5.4 meters, and the time delay was 0.2 seconds, you might be asked to calculate the velocity. So to do this, you just use the speed equals, I'm just going to fix up that too, speed equals distance over time rule. If this here is your length, then the distance that the sound wave and reflected sound wave travels is twice that, because it has to travel there to the prey and then it has to travel back to the dolphin. So I'm just going to write over here v equals distance over time, and we're working out the velocity of the wave, so we'll just put v equals 2 times L. It's really bad too, I can't draw any 2's in this video, and divided by time, and then sub in our values, which will be 2 times 5.4, which will be 10.8, and then divided by 0.2, and our velocity will end up being 54 meters per second. So that's how fast the wave is travelling. Sonar, which is sound navigation and ranging, involves the emission and detection of pulse sound waves. So this is very similar, it's the same principle as echolocation, and it's just used to map things like the ocean floor, and this is done to study plate tectonics, ocean currents, marine ecosystems, and so on. So what will happen is a ship will emit a pulse, and this pulse will be reflected, or this pulse will propagate to the floor of the ocean, and then it will be reflected by the floor of the ocean. The ship will determine or detect the time delay between emission and reflection, and that will be used to determine the distance to the ocean floor, which is the source of the reflection, and then that'll be used to map topographically the ocean floor and how far away it is from the surface of the ocean or the sea level. Ultrasound involves the emission and detection of high frequency sound waves via a transducer. So what will happen is an ultrasound will emit a bunch of different frequencies, and these sound waves of different frequencies will penetrate the body. Different frequencies will be reflected at different boundaries between different tissue types. So between when there's an interface between two different densities in tissue, different frequencies will be reflected. The transducer will detect these reflected sound waves, which will each be coming back, so the different frequencies will be coming back at different times depending on when they've been reflected, and the transducer will convert this detected or these detected pulses into an electric signal, which then forms an image. So the image displays the distances and intensities of the echo on the screen, and this forms a two-dimensional image, like black and white image of, I don't know, a baby in a tummy or something else, some other body part, depending on what is being investigated. Reverberation is when reflected sound waves accumulate and persist in a medium after a source dissipates. So, for example, in a concert hall, the medium would be the air of the concert hall, and the sound waves of like an orchestra or something like that will bounce and be reflected off the ceiling, off the walls, off the floor, etc. The energy of these waves or the amplitude of these waves will be decreased because the material of the roof, the walls, the floor will absorb some of the energy of the waves, but the reflected waves will still interfere with the new source of waves. So, like when the orchestra is moving on to a different note in a musical performance. This can have positive and negative effects. So sometimes, if the room is engineered correctly or appropriately, then it'll make the sound just sound amazing. But it can have negative effects as well, where the sound is interacting in a way that makes it sound really terrible. So it just depends on how the room is designed and engineered by sound engineers.